I think many of you are still joining. So let's wait a couple of minutes for others to join. And meanwhile, you can ask me if you have any questions from our previous discussion. If you remember, last time we talked about approximate inferencing, and we talked about two methods. One is random sampling, and second is rejection sampling. So we had seen how we generate random samples using the probability distribution that we have learned for the given Bayesian network. And we use this probability distribution along with some randomly generated numbers to generate new samples. And we said that after the samples are generated, the samples are true to the distribution, and then you can use those samples to count the occurrence of random variables, and based on that, you can answer inference query. Rejection sampling was slight improvement over random sampling in the sense that if the evidence variable is not present or the value of evidence variable is not same as the query, then in that case we reject that sample so that we save some time. But we have seen that in worst case it would act similar to the random sampling. We will see two more methods today. One is called likelihood weighing, and second is very important method called GIP sampling. It has many other applications also. We will revisit GIP sampling for other tasks also. So very important algorithm which we will discuss today. And with that, we will also talk a bit about separation in Bayesian network, like how to calculate joint distribution and all that. So maybe some fundamental questions would be answered today. So any questions, any doubts on what we had discussed so far? Okay, then let me share my screen. Is the screen visible? Okay. And let me also open the note that we want to discuss today. So I will juggle between a couple of notes. So approximate inferencing, why? So justification is, as we have already discussed, exact inference over Bayesian network requires order of a raised to n computation. There have been some efforts to propose better algorithms like variable elimination and all, but we know that it still remains a NP hard problem. On the contrary, we know that Bayesian network is a generative model, so we can generate sample using sampling techniques and use those sampling for performance to perform inferencing. And we approximate any desired conditional or marginal probability by empirical frequencies. So that way we can save some time. That was the idea of approximate sampling. We had seen this example last time, random sampling with the example of burglary, earthquake, alarm, John call, Mary call, and all that. So I've prepared this as an assignment, but I'm not sure whether you want to do it or not. So do you want to try this? We have already tried one example last time. So should we repeat this, or you are comfortable with this? Do you want me to give an exercise? Maybe 5-10 minutes you can solve it, or it is clear? So tell me if you want to do this exercise or it is clear. Okay, I think some of you are saying it is clear. Okay, so if it is clear, then we can skip that part and we can go to the next technique that we want to discuss. So the next technique that we want to discuss is called likelihood weighing technique. Idea is that we know that if a variable value is not consistent with the query, then that sample cannot be used. So fix the value of evidence variable as per the query. So apart from random sampling technique, all other techniques that we are discussing has evidence value same as the inference query. So do not sample the evidence variable, fix the value given in the query, weight the sample with the probability of the value assigned to the evidence variable. We will see what it means, and sample other variables using random sampling technique. So for example, the probability question that we query, inference query that we want to answer is probability of J given not M and not E. So probability of John calling given that Mary has not called and there was no earthquake. If you want to answer this question, then the sample that we want to generate should have value of M and E 0, because we are already given that M and E is 0. So this is what we mean by the first sentence here. Do not sample the evidence variable, fix the value given in the query. So which are the evidence variable in the query? M and E, Mary and earthquake. And the value given in the query is not M and not E, means that Mary has not called, or Mary called value 0 or false, and earthquake value false. So we will not put this, we will not sample this variable, we will fix them. So something like this. If you can see in this table, I have marked value of variable E and M to be false. So if whatever sample I generate, I always keep value of E and M false, because that is what I want to infer. The inference is based on that value. So that will be false. And now I need to sample only three variables, B, A, and J. So first benefit of this technique is now the sampling efforts are reduced. You are not sampling all variables. Rather, the inference question variables are fixed. But then, if you look at the samples generated, you might end up feeling that M and E are always false, which is not true to the distribution. Distribution says that E and M takes value false with certain probability. So if you look at the 1,000 examples, then out of 1,000 examples, only 998 times earthquake will be false. Two times you might see earthquake to be true. Right? That is what probability of earthquake tells us, 0.002. And similarly, if you look at the Mary calls, then Mary calls with certain probability, given the value of alarm. So if alarm is false, then Mary calls with a probability of 0.01. So 99 times Mary will not call, or Mary calls will be false, given that there is no alarm. Right? So this is not the complete distribution. We have fixed E and M, but we have fixed with some weightage. So instead of putting all sample with a probability of 1, we add weight along with the sample. How do we add that weight? That we will see now. But any questions so far? What I have said is E and M. We are fixing E and M because it is given to us. Inference question says that Mary calls is false and earthquake is false. That is why we have kept them false for all our examples. And we sample only B, A, and J. And then we will assign this weight to the sample generated, because this M and E remains false with certain probability. So we'll add that weight, probabilistic weight, with the sample. Is this clear? Any questions? Okay, I guess there are no questions so far. I will go ahead and I will again ask if there is question. So now let us see. So we sample B, A, and J. How do we sample B and J? Same as random sampling. we will do the same thing as whatever we did for random sampling. That is, generate a random number and see in which area of the probability the random number falls, and based on that assign value. Start from the top node and reach to the bottom node of the graph. So first sample burglary, then sample alarm, and then sample John calls. We'll not repeat that, but let's say for our first sample, burglary turned out to be false, alarm turns out to be false, and John calls also turns out to be false. So the sample that we have generated is F, 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 all five variables false. So if you sample 1,000 numbers, if you generate 1,000 samples, or if you take 1,000 samples from the data, how often you will see a sample with all false value? What is your guess on that? So that guesswork will decide the value of weight. So let us see that alarm becomes false given that B and E are false. So how likely that alarm will be false given that B and E is also false? So for that we will look at the last column of probability of alarm, which is 0.001. So alarm is true with a probability of 0.001 when B and E are false. So alarm will be false with a probability of 0.99, right? Or 0.999 rather. Yeah, 0.999. So alarm will be false with a probability of 0.999. And similarly, earthquake will be false with a probability of 0.002. Sorry, earthquake will be false with a probability of 0.0002. Earthquake will be true with a probability of 0.002. So earthquake will be false with a probability of 0.998. And second variable which we have frozen was Mary calls. So Mary calls will be false with a probability of 0.99 given that alarm is false. Alarm is sampled, so we will not attach probability with alarm. So the weight of the first sample will be 0.998 into 0.99. Which are these numbers? 0.998 and 0.99. Probability of seeing earthquake is equal to false, and probability of seeing Mary calls is equal to false given that A is false. Right? Similarly, second example. Let's say the second sample gives the value of B is equal to F, A is equal to true, and J is equal to true. E and M anyway remains fixed as false. Now let's try to associate weight with this sample. So we need to fix weight for E and M, the variables which are not sampled. So E remains false with a probability of 0.998. Now M remains false given A is equal to true with a probability of, if you see the first row of this table, then it remains true with a probability of 0.70. So it remains false with a probability of 0.30. So the weight of this column will be 0.30. Similarly, for third sample, the third sample is true, false, false. Again, if you calculate the weight, it will turn out to be same, 0.998 into 0.3. And for fourth sample also, the weight will be 0.998 into 0.99. Have a good look at this. Understand how we have calculated this weight. I will wait for a minute and please ask me if you have any questions on this. To calculate weight, we look at only two probability values, probability of E and probability of M. Is this clear? Any questions? Let's see if there is- Okay, Bhavik says, please explain again. Priyank says, need to multiply weight of E and M. Yes, Priyank, we will need to multiply those weights. Okay, you want me to, Urjit says, repeat with some pointers. Okay, yeah, maybe you're not able to follow it on figure. Okay, so let me repeat it with a pointer. Okay, so is the pointer visible now? So we are, let's say we are calculating this first sample, and the inference question is probability of J given not M and not E. So what we have done is we have kept M is equal to false and E is equal to false throughout our sampling process. Or in other words, we do not sample E and M because we know that it has to be false. Only then we will get the sample that we are looking for. So keep E and M false and sample only remaining variable B, A and J. Sampling for remaining variable would be same as the random sample. We will assign probability, we will generate a random number, and based on that, we will find out the values. So let us say the first sample has B is equal to F, A is equal to F, and J is equal to F. E and M anyway we have chosen to be fixed. So the samples that we have generated will not be true to the distribution now because we have chosen two variables, E and M. So how true they are to the actual distribution, or how do we want to weight them? So for that we associate a corresponding weight, and that weight will be equal to the probability of E and probability of seeing E is equal to F and M is equal to F given value of other random variables B, A and J. So if you see here E is equal to false, our distribution says that the random variable E, earthquake, is true with a probability of 0.002. So E is false with a probability of 0.998. Right? And similarly, the other random variable M, Mary calls, is false given that A is also false. So given that A is false, Mary calls remains true with a probability of 0.01, the second row of the Mary calls conditional probability table. So Mary calls remains false with a probability of 0.99. Is this clear, Urjit?
Yes, sir.
Okay. Yes says why we not compute other possibilities. A very interesting question. But I want to see if anyone else can answer this. So why are we calculating the weightage only for the variables which are not sampled? And why not for other possibilities? So one reason for this is, yes, is that because other variables are not fixed, so you believe that in your sampling process, it will become true or false with the given probability value. They will take true or false value as per their probability because we have divided the stick in the region of probability. So if something is true with a probability of 0.1, then out of 10 times, one time it will automatically come down to be true. Right? So that's why we believe in generative model. So that's why we don't need to assign weight for other samples. But for these two, which we have fixed, we know that they can take value true, which we do not want, but they can take with certain probability. So that probability is factored in the weightage. So when I say that I have sampled it, when I say I have sampled the first sample FFFFF, I know that I will see this sample 999 times out of total 1000 experiments. So that's why something 0.998 into 0.99 will be the weight, right? So similarly, we sample all of this. So any questions, Urji? This is clear? Is the table clear now?
Yes, sir.
Okay. Is it clear to everyone? If this is clear, then we are almost done. So I will just wait to see if it is clear to everyone or not. Bhavik says, what is the use of weight? We'll discuss that. We'll discuss the use of weight and we are done with this method. Yes, says yes. Then for others, we simply 1 minus value which is computed. No, yes, I didn't understand what you are saying. Then for other, we simply 1 minus value which I have which is computed. Or maybe, but you can think that it is multiplied by 1. So 1 multiplied won't change anything, right? Other possibility of what? Yes, can you unmute and tell me what you are looking for? Okay, I think you got the point. Okay. So let's come to the final part of this algorithm, which Pavan is asking, then what is use of this weight? So now when we want to answer the inference question, that probability of J given not M and not E, what we do is, again the formula remains same, count how many times J, not M and not E appear together, divided by number of times not M and not E appear together. But now you do not have the full data because you have fixed the E and M variable. So instead of counting it as 1, you will count this weight value. You will count them with weight value. So number of times J, not M and not E came together is this probability. So if you see how many times this happened, J was true and M and E was false, then there are 2 examples, 1 and 2. So instead of putting 1, you will put weight value there. So 0.99 into 3 plus 0.998 into 0.99. Divided by the number of times not M and not E were together in your sample. So not M and not E were together in all 4 of the samples. If you have done more sampling, then more numbers, but sum of all weight. So this will be sum of all weight values. Denominator will be sum of all weight values. So 0.998 into 0.99 comes twice in our example. So I did multiplied by 2. And 0.998 into 0.99 also comes twice. So I have put multiplied by 2 in example. So this will be something like this. And the final answer will be 0.2. Sorry, 0.5 or 1 by 2. Right. So this is the probability of seeing John call, given that Mary has not called and earthquake has not happened. Right. So this is likelihood weighing. I'm waiting for a minute so that if you want to note down, you can note down. And if you have any questions, have a look at this calculation and ask me if you have any questions on this. Is this clear? Yes, Pavik. Okay, what is the denominator if J given M not E is asked? Bhavik says basically weight puts its effect into the calculation which we assume constant. True, exactly, yes. And Keval says, what is the denominator if the question is probability of J given M comma not E. Okay, if it is M comma not E, then denominator will have M is equal to true. Instead of this false value, instead of this false, M will be true in the denominator as well as in the numerator. And in that case, your sampling will have fixed value of M is equal to true. For all this, you need to fix M is equal to true. And this will also change the corresponding weight value. So instead of 0.99, this will be 0.01. Instead of 0.3, this will be 0.7, and so on. Right, Chetan? Priyank says, so table should be different, fixed values change. Yes. So for the likelihood weighing, as I said, apart from random sampling, for all other sampling, the samples are generated based on the inference question. So depending upon the inference value, you fix the random variable. So for every inference question, you need to generate samples and answer the query. Dave says, what is the probability that our answer is correct? Because it is approximate answer. Yes, it is approximate answer. And usually, this is toy example, so we are answering based on 3-4 samples. Usually thousands of samples generated before actually we answer. And this correctness is measured with the closeness of the real distribution. So larger the number of samples, more closer would be the probability value to the actual distribution. So your answer would be closer to the exact inference as you generate more number of samples. Have I answered your question, Dev? Yeah. Urjit is also saying, yes, table varies based on various asked questions. So, yes, we generate sample based on inference. And this caveat also, like it can, like if you generate only 2 samples, then your probability will be very high, which is not correct to the actual distribution. Even in this example also, if you see, what we are saying is, earthquake has not happened, Mary has not called, but John is calling with a probability of 1/2, which doesn't look very real, right? If you look at the real probability of John calling and Mary calling, given that alarm didn't happen, this doesn't look very promising. So actually, if once you generate thousands of samples, then it will reduce and it will be more closer to the actual distribution. But this is the idea. Idea remains same. And for us, it is difficult to compute the thousands of samples, but for program, it happens in fraction of seconds. So through programming, you can do it very quickly. So this was likelihood weighing scheme. Any question on this? I think it is clear to everyone now. So we'll move to the next part. Okay, so before we move to the next part, which is a very important algorithm called Gibbs sampling, I need to tell you a bit about deseparation of the Bayesian network. So intuitively we know that, but some clarity is required. Let me go back to another part of the question. Somewhere here. Not this one. Yeah. So let's talk about conditional independence. So do you see the slide of conditional independence on this screen? Though we have talked about conditional independence, but some formulation of this is important. So we'll talk a bit of mathematics behind that. So let's say, given this graph, the red color graph, given this graph, red graph, we are asking few questions about independence of this random variable. So first question is, are D and E conditionally independent given C? So before we answer, first let us understand what does it mean. D and E conditionally independent given C can be formulated like this. Probability of D given EC is equal to probability of C. That means that probability of D does not depend on E, given that the C is there. So given that you have observed C, you don't need E to calculate probability of D. And similarly, to calculate probability of E, if you are given the value of C, you do not need value of D. So are D and conditionally independent given C in this graph? As we had seen earlier also, they are conditionally independent in this, right? We know that, sorry, this part, D and E part. We had seen this in naive-based classifier also. We said that D and E are independent. They depend only on C. But let's find out a procedure to do that. So procedure to answer this question is something like this. It is a 4-step procedure. Step number 1 is draw an ancestral graph. So ancestral graph contains all the random variable in the question, here D, E, and C, and their parents. That's why they are called ancestral graph. So D and parent of D, that is C, E and parent of E, that is C, and parent of C, that is A and B. So this becomes ancestral graph of this inference question or this query. Probability of D given EC is equal to probability of D given C. So ancestral graph is node and their immediate parents. Second thing is to moralize the graph. Moralize means get their parents married. So connect parents. So it becomes A, B, C, D, E, and A and B, there is a link between A and B, so they are connected. That is second step. Third step is disorient. Remove the directions, and remaining graph is a undirected graph. Step number 4 is delete the given in the question. So our question was, are D and E conditionally independent given C? So given was C. So delete the C from the graph, from this graph. So once you delete the C, what you are left with is A, B, D, and E. And now see that if there is any path between the random variables that you are looking for, the question was, are D and E conditionally independent given C? So after this 4 step, whichever graph you have created, see that is there any path between D and E? Answer is no, right? There is no path between D and E. So it means that D and E are conditionally independent given the variable C. So through algorithm also in a Bayesian network, you can decide conditional independence. Of course, so far we have done it through visual inspection and through some probability intuition. But while you are writing the programs, you might need some procedure. And this is the procedure, 5-step procedure. I will repeat the procedure once again. First, draw the ancestral graph, which contains the random variable in question and their parents. Moralize them means connect the parents. Remove the ages because ages doesn't matter. So disorient and delete the given part in the query. So given the variable, whichever variable you are studying, remove that given variable. And in the remaining graph, if there is any path between the pair of random variable for which the question is asked, then they are not independent. If there is no path, then they are independent. So in this case, there is no path between D and E, hence they are conditionally independent given C. Is the procedure clear? Let me see if there is any query. Okay, I think it is clear. It's fairly simple, but of course, this is interesting. We'll need this also, and this is interesting also because sometimes we need to programmatically decide this. So for that, we need procedure. So let me ask another question. Are D and E marginally independent? So what do we mean by marginally independent? That probability of D given E is equal to probability of D. So you don't need E to calculate probability of D. And similarly, to calculate probability of E, you do not need D. So that is the question. How do we do this here now? Same, we are asking for the same Bayesian network, this red color network. The question is asked for the same network. But now there are only two variables D and E, and we are looking at the marginal independence. So not given C. So C is not given. So what will be the ancestral graph now? Ancestral graph will be DE and parent of DE, that is C. C was not part of the query, so parent of C are not required. So ancestral graph, moralized, disoriented, everything, and then you are left with this thing, C, D, and E, unconnected, ages between C and D and C and E. Delete the given. So nothing is given here. We are asking about marginal independence. So nothing is given. So nothing to be deleted. And this is the graph we are left with. So now what question we ask? Is there a path between D and E? Answer is yes. There is a path between D and E. And that is why D and E are not marginally independent. Right? So also this will help us in understanding the difference between marginal independence and conditional independence. Conditional independence is given some variable, they are independent. Given that you have seen the C, D and D are independent. But if you ask that whether D and D are marginally independent, then I will say no. Right? Hold on here for 1 minute and ask me if you have any questions. But if you have understood it properly, then there was a reference we have made to this earlier. I will bring it. I will bring it and discuss that. But before that, I would like to see if you got it or not. So ask me if you have any questions on this. Is this clear to everyone? I think many of you are not answering. Tell me, is this clear, or also tell me if you have any questions. Okay, Urjit says that can you talk about the marginal independence again? Okay, yes. Okay, so yeah, let's talk about this. So remember our discussion from, let me do it here. So remember our discussion of naive-based classifier when I said, let me draw a cartoon. When I said we calculated it as follows, right? Probability of C given x1, x2 is equal to probability of x1 given C into probability of x2 given C into probability of C divided by probability of x1, x2. We did something like this. right? This was our model of naive-Bayes classifier. And I said that by calculating the denominator, I said that we need to marginalize this, and you get something like this: x1, x2, c is equal to 0 plus whatever value of x1, x2 is plus c is equal to 1. So for all value of c, you need to do this. Remember, I said that denominator cannot be directly calculated, but you need to marginalize. So idea was the joint distribution of x1, x2, and c can be calculated as probability of x1 given c into probability of x2 given c into probability of c. And why? So I said that look at this graph and see that c is independent, x1 depends on c, x2 depends on c. That's why it is something like this. But now we have a procedure to calculate this dependence. Now what we ask, the question we ask is C marginally independent? Is x1 and x2 conditionally independent? So we need to look at this and we need to know this. So we just did so far through visual evidence only, but now we know the procedure. Then is x1 and x2 marginally independent? So if the answer of this is same, let me put formula for here. So then if xc is marginally independent, then probability of c given x1, x2 becomes probability of c. If x1, x2 are conditionally independent, then probability of x1 given c comma x2 is equal to probability of x1 given c, and probability of x2 given c comma x1 becomes probability of x2 given c. So this is because of this conditional independence. This is because of this marginal independence. And had x1 and x2 be marginally independent, then probability of x1 given c comma x2 would become probability of x1. Probability of x2 given c comma x1 would become probability of x2. So had they been marginally independent, I'm just giving you a cue. Had x1 and x2 be marginally independent, this probability could have been calculated as x1 into x2. Which I said then that don't do this, this is wrong. But they are not marginally independent, that's why we cannot calculate like this. That is why we need to bring C into the formula, and that is why we have to use these three together to calculate probability of complete distribution. So if I want to describe this graph of C, x1 and x2, then I can say that C is marginally independent, x1 and x2 are conditionally independent given C. And that is why the three probability values to count x1, x2, and c is probability of c, probability of x1 given c, probability of x2 given c. Multiply them and you get the answer. If you drop the naive assumption, then x1 and x2 are also not conditionally independent, and then it becomes more complicated. But that's why we made naive assumption, and we assume that x1 and x2 are conditionally independent given c. So marginal independence means to calculate this probability, you don't need to look at other variables. Conditional independence is variables are independent given value of some other variable. Right? So this was something important, but I think if I discuss this at the beginning, then it might sound boring. But now, once you know all the models, this would be an interesting discussion. So, have I answered your question, Urjit? Is this clear to everyone now how we calculated the probability and why? So, earlier I just told you about look at the graph and look at the arrow and calculate the joint distribution. But now we know the procedure behind that. Okay, I guess this is now clear to everyone. And this procedure is important to be introduced here because as the Bayesian network becomes more complex, the visual inspection also becomes difficult. And in that case, you need to rely on program to look at the graph and find out the conditional and marginal independence and calculate everything, calculate all the probability. So that's why also this independence is required. Few more examples before we wind up. So we talked about D and D marginal independence. Now let's talk about. So if you see, I have given this formulation here. So probability of DE, you cannot write probability of DE as probability of D and E because they are not marginally independent. Had they been marginally independent, then yes. But you can write something like this: probability of D, C, and E, that is probability of D given C into E given C into probability of C, given all outcome of C, because C is marginalized. And that's why we say that we marginalize a variable. Right? The context was in marginal independence. That's why the word marginalized was used there. So D and E in this kind of graph, D and E are conditionally independent given C, but marginally they are not independent. So to calculate their probability, you need to bring in C, marginalize it, and get the answer. So let us answer a few more questions to make everything clear. So are A and B marginally independent in the graph? So which graph? The first one. This. So are A and B marginally independent here? Visually it is very easy, but let's try the procedure also. So remember this graph. What do we need to do? Let me repeat the step and then we'll see the calculation. The variables under the query are A and B. So we need to create a graph of A, B, and their parents. So there are no parents, so graph would be very simple. Graph will be only A and B. And there are no parents, so there are no connections. So there are no connections, so it means that you don't need to moralize or disorient or anything. Just two random variables A and B, not connected with each other. So answer for that will be, are A and B marginally independent? Answer is yes. Second question is, are A and B conditionally independent given C? This is an interesting question. First, let me see if you can get the answer. For the same graph, the question is, are A and B conditionally independent given C? We are asking for the same graph. What is your answer? Okay, Priyank and others. Priyank says yes. Bhavik says no. Yes says yes. Okay, let's see. So do the procedure. We have asked about A, B, and C. Now there are three variables in question. So draw a graph of A, B, C, moralize parents, disorient, and remove the condition part and see what you are left with. So it becomes something like this. Finally, you will get this graph because you have moralized it. So A and B becomes connected. So given C, A and B are not independent. And the question is something like this. If you want to calculate A given B comma C, then you have to calculate A given C. Here, if you want to calculate probability of A given B, it is equal to probability of A. But this is becomes probability of A given C. So this is where things becomes a bit tricky, right? So there is a slight difference. So it is possible that marginally independent, the A and B are marginally independent, but they are conditionally not independent. They are conditionally dependent. Given that you have observed C, they become dependent. So if you want to semantically understand this, we can look at our burglary example. So burglary and earthquake are two independent events. So burglary and earthquake were marginally independent. But given that alarm has rung, given the alarm, burglary and earthquake becomes conditionally dependent. Because you have heard the alarm and you know that it is not burglary. So you can decide that alarm might have rung because of earthquake or other way around. You have heard the alarm and you know that there is no earthquake. So you infer that the alarm might be because of the burglary. So given that you have observed C, you can decide about A and B given one. So they become conditionally dependent then. So they are not conditionally independent. Right? Let us see if you have any questions on this. Yes, he's asking, do we need to moralize? Yes. So that is the procedure. So you need to moralize. One more question. Are A and D conditionally independent given C? Let's see what we are talking about. We are talking about A and D. We are talking about A and D given C. We are given C and we are asked whether A and D are conditionally independent or not. So we'll take a graph of A, C, and D, moralize it, and see what happens. Finally, we remove the C and figure out whether they are independent or not. So are A and D conditionally independent given C? So after all the four steps, the graph we are left with is A, B, C, D. Finally, remove the question variable, that is C, remove C, and what you are left with is two separate graphs of AB and D, where there is no path between A and D. So we can say yes, A and D are conditionally independent given C. And one more question, are A and D marginally independent? Again, the graph will be same, but now C is not under the question, so you will not delete the C. And that's why answer will be no, they are not marginally independent, because if you keep the C in the graph, you have a path from A, C, and D. So answer to this question is yes. Answer to this question is no. Right? Yeah, so that's the whole story. I will wait for a minute and then I will tell you why all this thing was required. Is this clear? Is this clear to everyone? Okay. So now let me tell you why all this story. So now if I'm given some graph like this, let's say very huge graph of so many nodes. Also notice that I'm not sure whether I have told you or not, but Bayesian network are always acyclic, because you cannot have a cycle of dependency. Otherwise, it will be very difficult to calculate. Now, one thing that we have discussed all this is So to decide about the value of any random variable, for example, let's say if I want to decide about probability of f given everything a to I, probability of f given a b c d e f g h I, then using my knowledge of conditional dependence and independence, I can say that probability of f, even though I don't know much about the graph, I can at least say this. Let me write this properly. Right? Do you agree with this? If you agree with this purpose of the lecture is out, if you agree, please type in agree. Like, do you understand this? Do you agree with this? Let's see how many of you are saying we agree. Okay, okay. Many of you saying yes. Okay. Let me show the formula again. Do you agree with what I have written here? Not getting messages. Okay, some of you are saying yes, but I'm getting messages late. Okay, so why this is important is because our, for those who are still confused, let me tell you. So why this works? Because to calculate f, now we know that given d, e, g, h, and I, f becomes conditionally independent of everything else, right? So given its first neighbor, f becomes conditionally independent of everything else, and this cover of first neighbor is called Markov blanket of f. This Markov blanket is very powerful idea because it helps us in calculating probability, joint probability in a very huge network. So even if the network has thousands of random variables, you know that to calculate probability of a particular random variable, you only need to look at the variables which are immediately connected to the particular random variable. That should be sufficient. For example, what will be the Markov blanket of E? Again, I'm relying on visual things, but you can start asking the question of conditional independence, marginal independence, and all that. So, is E conditionally independent? First, is E marginally independent? Answer is no. Is E conditionally independent given B and C, or given B and C is E independent? Then, given F, is E independent of G? Answer is yes. Given F, is E independent of H? Answer is yes. Given F, is E independent of I? Answer is yes. Given B, is E independent of D? Answer is yes. So what you are left with is this blanket. This green area is Markov blanket of E. Immediate parents and siblings and children. That makes a Markov blanket. So if you want to calculate outcome of E, you only need to look at B, C, and E. Right? That is Markov blanket. We will talk about this more next time, and this will help us in understanding this powerful concept of Gibbs sampling. I will wait for if there are any questions. A probability E given BCF. Okay. Yes, probability of E given BCF. You need to, if you want to calculate, not probability of E given BCF, but probability of E given everything else reduces down to probability of E given BCF, yes. Yeah, so this was idea of Markov blanket and conditional independence in Bayesian network. We will explore this to discuss gift sampling in the next lecture. I will stop here.
Hello, good afternoon, everyone. Am I audible to you all?